is what I want to. Well, 15.7 we did last time. Let's do 15.6 today. Okay, and so these are integrals in mass calculations. It's kind of nice what your book does in that they lump together into one section what a lot of books will do in several sections as you go through Calc 1. They hit you with them as you go. Your book kind of waits until you can tell the whole story, which is what we can do now with the machinery we have. I think that's kind of nice. So we'll tell it in one day. And so we're going to start off, your book calls it the playground law. And so, because you have a seesaw, and we all know how the seesaw works, right? And so you have a stick figure, right? But what we're going to do is we're going to make him a modern stick figure. He's big. Right? And then let's have a traditional stick figure. And they balance. Why? How do they balance on the seesaw when you have big stick figure and little stick figure?
The distance is pretty difficult.
Yeah, right? You got to take into account that distance, right? So if I call that D1 and his mass is M1, right? The point is that M1D1 has to equal, I guess I'll call it M2D2, right? Where D2 is this. Who was the Greek that said, "Give me a fulcrum and I'll move the earth"? Archimedes? One of the big three. It might have been, yeah. So, this concept comes into play in this section. As a matter of fact, your book talks about this right away. So let me jump to it. Here's your book's take on this. Integrals for mass calculations. Yeah. If you have, it says, intuition says, if you have a DVD without a hole in it, so a thin circular disc, you can balance that, right? Right at the center. The balancing point of this book. Is this possible? Did I impress anyone? Guess not. Just for the sound. All right, but the idea is any thin surface, you might have what we call a center of mass, right? And that's a kind of a classic application of the kinds of integrals that we're dealing with here. So we're going to be talking about that center of mass, or centroid, today. And actually, it's useful in physics because, when you, even here, right? When we talk about, the relationship between these two boys on the playground, right? We don't really worry about, does this kid have big arms or big legs? No. We treat him as a point mass, okay? This is done all the time in physics. You treat something as a point mass. And if you want to know where the point mass should be treated, that point would be the center of gravity, or the centroid. Okay, so this is kind of one of the main ideas, I guess, behind some of these calculations. So I thought we'd go through some of these quick checks as we kind of go through, because that's always the first part of your homework. So why not get some of it done now, right? So, moving along, they talk about the seesaw too, and they say, here you go. A 90-kilogram person sits 2 meters from the balance point of a seesaw. How far from that point must a 60-kilogram person... so this is... and assume the seesaw has no mass. That's important also, right? Because if the seesaw is heavy enough, it might not... You put the two kids on it, might not matter how big they are, the thing's not moving, right? So we're going to assume that it's significantly lighter than the objects that are placed on it. But yeah, we're following directions here from the problem I just gave you, right? So let's see. I guess we'll work it out because I promised to do some homework. Here we go. M1D1 equals M2D2. So we have, well, the bigger one, 90 kilograms, right? And the distance is 2 meters. And over here we have a 60 kilogram person. And the question is X meters, right? So that's, yeah, we're not really doing high-powered mathematics here, are we? I'm getting 3 meters. How about you guys? All right, 3 meters. We're 1 for 1 today, guys. Moving on. Where's the calc, Paul? Where's the calc? All right, so we want to generalize this. And so we have a coordinate system. So here's a nice picture. Oh, I like it. An applet. Drag the two masses to change their positions. Okay, let's do that. This is going to crash my computer, isn't it? We've seen this happen, right? I mean, in theory, that's a really nice thing to have, right? But I didn't see anything happen, did you? Oh, maybe drag the mass itself? Oh, okay, cool. So I just made this, I made the kid grow. Oh, yeah, oh, look at that. That's nice. So by the way, what is this? This X bar. We're calling it the center of mass, right? The center of mass. So, okay, so let's do something here. Let's put the masses the same distance from 0. Oh, okay, so they're both 2 away from 0, but that doesn't fix it. The only way I can get the center of mass to be at 0, right, is if I modify the mass until the masses are the same also, right? So we understand this? So what changes the center of mass more? Changing the mass or changing the distance? Let's see. If I move the distance 1, okay, or if I move it 2, looks like a 2-to-1 ratio the way it is right now. Well, that's because I started 2 away from the center. So there's a real reason there. If I change the mass, let me change mass 2 a little bit. So this is a real nice applet, I think. You can play with this a little bit when you guys are at home if you want. Okay? But what we did was we used the fact that mass times distance has to equal mass times distance. And if we imagine the balance point, again, where you put your finger to balance the balance beam, right? Call that X bar. Okay? The center of mass of a 2-mass system is given by this. Notice the denominator is total mass, right? The numerator, those are called moments. Okay? Now, these are called moments around the point, the origin. Later, when we up it a dimension for Calc 3, we're going to talk about other moments. And I guess I'd be curious to hear if you've heard of these other moments in physics class. Like we'll have moment around the x-axis or moment around the y-axis. Have you guys done that at all? How many have? Can I see a show of hands? So some of you have. Okay. So, but do you do any integration when you do those things? In statics you will, because they kind of assume you've seen this or are seeing it now, one of the two. So that's interesting. Okay, so we'll get to that today then, right? Oh, here we go, quick check 2. Let's work through it. Because, I mean, QC1 was painless. Let's see if we could do QC2. Here we go. Solve the equation for x to verify the preceding expression for the center of mass. Oh. Well, you can do that. I'm not doing that. Right? Do you need help with that one? I mean, I guess you didn't need help for number 1 either. But basically, solve this equation for x bar. All right, and they give you the answer, so we're good. Wow! That's better than my drawing. All right, number 3. So next they say, What if you have lots of objects on the line, not just two? See, I like the progression. Well, we have so many that we're going to bring the Greek letter sigma there, right? And now x bar looks like this. With me so far? Okay. You'll notice I have a big sum up in the numerator, and I have a big sum in the denominator also, right? Now, what's the game in calculus? Anytime you have a sum, especially if it's a Riemann sum, then what do we turn it into very shortly? We're going to turn it into an integral. Okay? So, I mean, what's the deal here? This is if you have n people on the balance beam, on the, and you're trying to calculate the center of mass for n objects. So here's 4 objects. They do the game again, right? But now what we want to do is we want to say, what about continuous objects? Because in real life, what's your engineer going to do? Well, he's going to say, look, I've got this kind of a picture. You're talking about statics. I'm picturing classic problem. I have a wall here, okay? So this is my wall. And I have a beam hanging out, right? So here's a beam. And will the beam hold? That's the question. I mean, I guess you have force being exerted, right? Where, though? Everywhere, right? It's not like there's just 2 kids that account for most of the mass. I mean, this thing's made out of steel, let's say. Right? Or maybe it's an I-beam. You know, I'm not that great an artist. But you see what I'm saying? So if the whole thing has mass, this is where instead of adding up the 4 points or the 2 points to get the center of gravity that we want to integrate. And that's what the book is going to get at next. So as we work through that, continuous objects in 1 dimension. Here we go. Okay. So now the concept of density comes into play. Mass per unit length. It says in figure 15.68, suppose A equals 0, B equals 3, and the density of the rod. By the way, do you guys know that Greek letter? That's rho. Yeah, that's the Greek letter rho. Okay, so it's the R, but that's what we'll use for density here. Rho of x is 4 minus x. So what's that mean? I guess it means that, well, let's draw the picture carefully here. Here, scoot over, book. Okay, so let's see. This is quick check 3. And so I have, again, my fulcrum. They drew this triangle. I have my rod now. And they say this is x equals 0, and this is x equals 3. And we say that that rho of x, right, so the density, rho of x, is 4 minus x. So that means that you have a lot of density, right, over here. Maybe it's heavier over here, right? Rho of 0 is 4. But when you get to here, rho of 3 is only 1. So it's going to get thinner. I almost feel like they shaded it wrong. Well, okay, they shaded it, but we just would want the opposite shading for our quick check, I guess. Do you guys see what's happening? We're saying that this is really heavy over here and not so heavy over there. Okay? So where's the rod the lightest and heaviest? I think that's what I just answered. Cha-cha. Heaviest at x equals 0, lightest at x equals 3. Using the slice and sum strategy, right? Riemann sums. We're dividing the rod into n subintervals. I've seen this game before. Let's open that up. See a little more. Ah, what is the mass of one of these little subintervals? Well, it's approximately rho of xk times delta x. We can't do that because the mass changes, right, as you move from left to right. But as the subintervals get smaller and smaller, there's not much change anymore in the density function. So this is where picking an xk is going to work, right? And so we go to our center of mass formula. There we go. Same thing. I have this rho of xk. This truly is a Riemann sum at this point, right? Because we're taking the limit as delta x goes to 0, which means n is going to go to infinity. And sure enough, we have a really nice integral formula. And this is the formula for the center of mass in one direction. Okay? So there's my formula. Capital M over little m. X bar equals capital M over little m. That's the way they write it. I guess I would usually write it as the integral formula. Okay, so to me, one-dimensional case. In one dimension, we can say the center of mass, x bar, is given by a fraction of integrals, okay? So we're going to integrate, I'll say, from a to b, and we have x rho of x dx over the integral a to b rho of x dx, okay? But again, just so we understand what's happening here, right? Little m, okay, is the mass. So when you integrate the density, that's your mass. But this, what's this? This is the moment, it's called. Moment. Guys follow so far? Okay. Moving on. They do an example, find the center of mass, but that's just integrating. Do you guys want to see that or move on? Move on. Okay. 2 dimensions. In 2 dimensions, now this is, we imagined the piece of paper, the lamina, the thin plate. So I want to jot that down for you guys so that you think about that. 2 dimensions. So now instead of a teeter-totter, we might ask the center of mass of a lamina. And that, again, is like a thin sheet. Okay? So where do I balance this piece of paper? Right? Actually, what's the answer to that? Where do you balance the piece of paper? Here, smaller piece of paper. It's rectangular. No. Okay, even smaller so we can see it. So where's the center of gravity going to be? The geometric center, right? So how would I find that? Yeah, you could fold it diagonals this way or fold it that way, right? There's lots of symmetry. If you fold it along any 2 of these lines, you ought to find that center, right? And then in theory, this will just balance there, right? See? Yeah, perfect. All right, that's the idea. Okay, so let's see. Well, we're going to generalize here. And so the mass is the integral of the density function, but this time the density function can be a function of 2 variables, right? Maybe this piece of paper that I have is more dense on one edge than it is on the other. Would that be true since I folded it? No, I don't think so. I think you're going to have 4 sheets basically anywhere. So I don't think this will make a whole lot of difference. Okay, but we have some kind of density function. You guys, some of the problems that you guys will work with, they'll tell you right off the bat, constant density, okay? Or call the density 1. Is that what they say for water? Water has density 1, and then you, right? So, again, I'm starting to get out of my league when I start talking physics, right? So, but they'll give you that, and then it's a matter of, simplifying things. So let's see what we have here. The center of mass in 2 dimensions now. You'll notice that the difference is that there are different moments. So you guys that have seen moments, is this the notation you're using also? My and mx? No. All right, so let's get used to that. So what does it mean? Okay. So in 2 dimensions, okay, the center of mass is a point we're going to call x bar comma y bar. We need to compute, basically, it's doing 2 of these calculations. Okay? So when you do x bar, you'll notice that we're doing the moment, okay, y. So x bar is my over m. Okay, moment with respect to the y-axis. So this is the same, this x bar, it's the same formula we had before. Okay, which shouldn't surprise you. It's x, rho of xy, dx, over the mass. Oh, but the mass this time, so there is an issue here, right? Because how do I get the mass of a 2-dimensional object? I can't do it with a single integral, right? I need a double integral of the density, and actually we'll need a double integral for the numerator also. And so that's where instead of a and b, we put an r. Okay? And so we have, you integrate rho of xy, and instead of writing dx, let's write dA. So here is a nice formula, which is a generalization of what we did up there, x bar. And I guess I could say, very similarly, y bar, what's that going to be? Take the moment across the x-axis, divide by the mass. So again, you have a double integral over a double integral. The difference is this one would be y times rho of xy dA, and then we divide again by the double integral of rho of xy dA. Okay? When you have constant density, like we did for this piece of paper, okay? Jesse called this the geometric center. I'd call that the centroid. So if you see the word centroid, I guess things are a lot easier, right? What is the bottom then? Like if the density is 1, see, whatever the density is, you could just call it rho. If this is a constant, right, you could factor it out. So the centroid, you could say, is given by this. X bar would be, again, it's still my over m. But it's, you could factor out a rho, and so you just get double integral of x dA. And the denominator, you factor out a rho, and so you get double integral of dA. And so what happens? Those are gone, right? So x bar you get by just doing double integral. And by the way, what's this denominator? If you do the double integral over r of dA, what is that? That's the area, right? We said when you integrate 1, so really I could say it's the moment across the y-axis divided by a. And then the other one's y bar would be the moment across the x-axis divided by a. So this is in the special case where your density is constant. And sometimes some of the problems will ask me that also. Questions so far? Okay. Moving on. Quick check 4. Explain why the integral for my has x in the integral. Explain why the density drops out of the center of mass calculation if it is constant. I guess I just did the latter part, right? I just showed you how the canceling happens. But for the former part, the distance from the point xy to the y-axis is x. Remember, this is the moment across the y-axis. And so, just like we were doing the teeter-totter, so let's show a picture of this 2 dimensions, maybe right up here. Here's the here's the pencil, right? And it's going to balance my sheet right at, the center of gravity. Well, the picture is, okay, if you just look at the sheet very carefully and you say, well, this is the x-axis and, this is the y-axis, let's say the y is in this direction. So as I'm measuring across, sorry, that's backwards, x-axis, y-axis. As I'm measuring across the y-axis, I want the distance to the y-axis, that's x, or the distance to the x-axis, that's y. It's almost like having 2 separate teeter-totter problems because you have these 2 axes that are perpendicular to each other. Okay, so we're almost ready for the final generalization, right? They do another example here. We're about to go to 3-dimensional objects. But rather than click on it, can we just go to the paper and imagine what's going to change? So tell me that some things that are going to change when I say center of mass of a 3-dimensional object. And maybe this is what I care about the most. If you like sports. Matthew?
Well, you're going to be doing triple integral.
Absolutely. Triple integrals, right? So, that's one thing, right? My formulas are going to involve triple integrals, right? So I can do a fraction and I can imagine already I'm going to have this. What else? What else is going to be different? We'll have a z component where? Well, all over the place, right? So for instance, remember what we were integrating down here? What was it we were integrating? Rho. This time, rho, the density, has to be a function of x, y, and z, right? And I agree with Matthew. These triple integrals, I think we've been writing what do we write for our d down here, maybe? And then dv? Or am I wrong? Is that what you guys have been writing? Yep, okay. What about up in the numerator? Well, okay, so my center of mass is going to be given by, and this is what Jesse was getting at also, right? We're going to have 3 coordinates, x bar, y bar, and z bar, right? So rather than write all of them, maybe I'll just do x bar. Now, when you integrate density, what do you get? You get mass. That still lives. In the numerator, we had what we called a moment. But in 3 dimensions, okay, if you're trying to find x bar, it's going to be the moment, the balance, if you want, across the YZ plane. You'll see this written, right? I think, well, that's what I would do. Let's see what your book does for notation. They're showing, yeah, MYZ. X bar is MY. Yeah, that's what I would do. Distances from the YZ plane. Quick check 5. Explain why the integral for the moment mxy has z in the integrand. Okay, so actually, this is a good question. Do you have an answer for it? Not yet. Okay. Maybe you can answer this. Do you know what my integral is going to look like in the numerator of this as I compute x bar? Yeah? Oh, go ahead.
But,
The other question, yeah.
yeah, since the moment of xy is distances from the xy plane,
Yes.
it actually means you're moving in the z direction.
Exactly. How far in the z direction did we move from this point to there? Well, that's your z coordinate, right? The distance from the xy plane to whatever point you're talking about is z. So again, mass times distance gives me the balancing point. So if I want the balancing point, take the distance, right? Take the moment and divide by the mass is really what we want to do. So again, you know, your formula here, right? They give you, I think they give you all of them here, right? There they are, right? So the moments are there. You have to divide by the mass. So my calculation is going to be something like this. For the center of mass of a 3D object. That's only x bar, right? For y bar, you put a y there. For z bar, you put a z there. So I think it's time for an example, for sure. And so the question is, what do we want to... Okay, so here's a classic example. Suppose I have... so let's imagine... a triangular... I said imagine a triangular plate, right? That's not really what I want. Yeah, I want a three-dimensional solid with vertices. Well, I guess there's 6 vertices I have, okay? A three-dimensional solid pyramid, let's say. That's what we really did. So you want to make the note for yourself? What are the vertices? Yeah, they're still here, but we also have another vertex at the origin. So the picture of the object, I guess, depends on the point of view. You know, it looked more like this. You had at the origin, we could connect in any of these 3 directions. And so, you know, see, that doesn't look right to me. That looks like, it doesn't look three-dimensional to me there. Right? I mean, I'm trying to make it look kind of like this a little more. That's a little better. But if I label that 4th vertex, it's from the origin out to these 3. That looks a little better. So find the center of mass of that object. Okay. So I guess there's a lot of calculations to do, but there's a lot of symmetry also. So I kind of feel like if I can show you how to find x bar, we'll probably get the answer. All right, so let's do that. Begin by computing. How about we begin by computing little m, the mass? Okay. So let's see. M is going to equal, well, whatever rho is, right? Because that's a constant we're saying. Right? We said constant, so that's rho. Times the triple integral over d. D is the triangular plate of 1 dv. Right? So I think the hardest part of all these problems is setting up the iterated integrals. Sometimes you guys have seen in the homework there's one ordering that works better than another. Here there's so much symmetry I don't think it really matters. I think I'm going to do it this way because I'm most used to z being a function of x and y compared to the other way around. Right? Does this make sense to you guys? So I guess the question is, what are the limits of integration here? Well, let's label these points. I think this is good practice. This is 1, 0, 0. This is 0, 1, 0. And here's 0, 0, 1. And I think maybe the easiest thing to do would be to work outside in. Because on the outside, when we do dx, the limits of integration are numbers, right? So what are they going to be? 0 and 1. Right? But the next step, when we look at y, these have to be functions of what? Functions of x. You guys with me? So maybe I'll draw, remember I mentioned I'm going to draw more than one picture. Let me draw just the xy plane for a minute and forget about z. I just want to draw what this looks like. If we didn't have any z involved at all, isn't it this line is the only thing on the plane? And it's going from 1, 0 to 0, 1, so that's the picture, right? And so when I say I'm integrating, I guess I'm going from here to there. That's the image. If I were to project this down onto the xy plane, that's the region I'm looking at. Yeah? So we're talking the lower limit is going to be 0, but when I say 0, I'm really saying y equals 0. And the upper limit up here, what's that going to be? That's this line right here, right? So that's going to be y equals what? Negative x plus 1. Because it's shifted up 1 there. And so that's what goes here. Guys with me so far? Okay, now how about dz? Well, same game, I guess. Looking at the three-dimensional picture, we want surfaces. The lower one is the xy plane. The xy plane here is given by z equals 0. The upper one is this plane. Now I need the equation of that plane. How do I get the equation of that plane? Well, maybe we could use a little help here. So the equation of a plane, one way to get it is ax plus by plus cz equals d, where the vector ABC is the what? The normal vector, that's right. So you guys, when we look at this plane, do you guys know what the normal vector is? I agree, 1, 1, 1. Now what if I didn't know that by looking at it? This one I can see it. If I didn't know that, here's one thing you could do. You could take this vector along that line and that vector along that line, do the cross product, and the cross product will be perpendicular to both, and you're going to get it. Okay? But it's 1, 1, 1. So if it's 1, 1, 1, that's nice because now I know this is 1, 1, 1. So we have ax plus, oh no, just x plus y plus z equals d. Any idea what d should be? Well, look at some of the points that are on the plane. X plus y plus z has to equal what? It has to contain these 3 points, guys. I agree. 1. I did not make up a very challenging problem here, okay? Let's just put it this way. This is challenging. Could have been a lot worse, right? So now, solving for z, I see that another way to write the equation of the plane is that z equals 1 minus x minus y. Yeah? So this I would write as 1 minus x minus y. And by the way, the one, I think Matthew gave me this one, negative x plus 1. We could have written it as 1 minus x. That might be what you said. I don't know. But it, again, same idea. So, working through, we're trying to get the mass. Let's finish the calculation, right? So let's see. I take the mass, and I say it equals, here we go, rho times integral 0 to 1, integral 0 to, I'll write 1 minus x this time. When I integrate dz, what do I get? Z from 0 to 1 minus x minus y. Right? So this equals rho integral 0 to 1, integral 0 to 1 minus x. And when I plug in z equals these things, I just have 1 minus x minus y. Need to integrate dy, need to integrate dx. This is rho integral 0 to 1. Okay, now how do I do this? I'm integrating dy, right? These are treated as constants, that's not. So what do you get as the new integrand, or what do you get? You get y minus xy minus 1/2 y squared as y varies from 0 to 1 minus x. And then we still have to integrate dx when we're all done. That's okay so far? So we have rho integral 0 to 1. When I throw in the 0 for y, everything's gone. When I throw in the 1 minus x, let's see what I get. I get 1 minus x times 1 minus x minus 1/2 of 1 minus x quantity squared dx. This big mess has to be integrated. Okay, running out of room. I'm going to go to the next page. Let's see. M is equal to rho times integral from 0 to 1 of what? All right, I better just kind of simplify here. This is a big mess. 1 minus x minus another x plus an x squared minus 1/2 of, and this is 1 minus 2x plus x squared. dx. This equals rho times the integral 0 to 1. Let's see, how many x squareds do we have? I have an x squared minus 1/2 of an x squared, so that's 1/2 x squared. How many x's do we have? Oh, they drop out, right? Because I have minus 2x and then I have minus negative 2x, so plus 2x, those are gone. And then I have 1 minus 1/2, so I'm getting minus 1/2 here, dx. Oh no, because we have half of a 2x, right? So minus 2x plus 1x, so there's a minus x in here, is that right? I think so, I think you guys caught it. Good job. Okay, now I'm ready to integrate. Here we go. This is rho times. Now when I integrate the first piece, I get 1/6 x cubed. And then when I integrate that x that you guys found, it's minus 1/2 x squared, and then minus 1/2 x. And this is from x equals 0 to x equals 1. Oh, okay. So I just get rho times 1/6 minus 1/2 minus 1/2. Right? Something I don't like about it, guys. It's negative. I don't like that. Right? That's a problem. Where's the positive?
You get 1
Up here.
Yeah, I'm going to get 6.
1 minus 1/2 is positive 1/2. I agree. So this is a positive 1/2 x, but this is a minus 1/2 x squared. And that makes this a positive 1/2. Is that better? So the mass is 1/6 of rho. Okay, I like that. So that's the mass. Wow. Half done. Well, kind of, right? I mean, look at the original problem. It said, let's find the center of mass. We found the denominator is 1/6. Now we have to do the numerator just to get x bar, then we still need y bar and z bar. But we're going to say we have it once we have x bar. So next, let's see if we can find the moment across the yz plane. So this is the triple integral, again over d, and again dA, but this time it's x times rho. Right? That's okay? So this is not going to be so bad because we're going to take the rho out, and so all we really need is the triple integral of x, and if we go dz, dy, dx again, okay, guys, for the first two integrations, we're treating x as a constant, right? So this equals rho times the integral from 0 to 1 times x, and then we have all this other stuff that we already computed, dx. Yeah? See what I'm saying? So this is going to be, based on my work above, rho times the integral 0 to 1. It's this with an x in front. So we have to integrate now 1/2 x cubed minus x squared plus 1/2 x, and then we'll have it, dx. So that speeds things up. Okay, moving along. This is rho times, let's see, 1/8 x to the 4th minus 1/3 x cubed plus 1/4 x to the 6th, right? I love zeros and ones. This is a great problem because now we just have fractions, right? So we get rho times 1/8 minus 1/3 plus 1/4. Sounds like some 24ths, right? 3/24 minus 8/24 plus 6/24 equals 1/24 of rho. All right. So, after all that work, x bar is myz over m, which equals, what is it? 1 over 24 divided by 1/6, because the rows cancel, is what? 1/4. Yeah? Does that make sense? If you believe that, then the center of mass would be, by symmetry, 1/4, 1/4, 1/4. Basically what I did, guys, when I did my computations, I wrote down M. Maybe a better way to look at this, write down V. Pretend that rho is 1, and let's do the same. I mean, I made up the problem anyways. Suppose the density was 1. Then you're really finding the volume when you did this calculation, right? I said it was constant. So we did this. Yeah, this is, if this is 1, then we're finding the volume. And we worked out and we got that the volume of the pyramid ended up being what? 1/6 of the density? Actually, do you guys know the formula for the volume of a pyramid? I do, I think. Isn't it 1/3 area of the base times the height? Right? So what's that look like? Well, again, the height of this thing, when I think about this as a pyramid, I guess, if I decide that this is going to be the base, B, then my height, h equals 1. Now, what's the formula for the area of the base? Well, that's a triangle, right? So it's 1/2, 1 times 1, right? And the height is 1. So you could see why we got 1/6. Okay, so the volume of the pyramid was 1/6. And now, when we computed the moment, again, pretend the density is 1, just ignore it because we ended up canceling anyways. We got 1/24 was the moment. And so we worked out that the coordinates of the center of mass would be 1/4 and then 1/4 and then 1/4. And now that makes sense to me. That's not on, you wouldn't expect the center of mass of a three-dimensional object to be on its surface. You'd expect it to be underneath. But where exactly? 1/4, 1/4, 1/4. That seems nice. We have that symmetry. Okay? So hopefully that was understandable. So let's do this. You guys have to find the center of mass of a lamina let's do this. Let's suppose that we have a triangle, and let's make it nice and symmetric, kind of like last time. So let's have the object, we'll put one vertex here at 0, 0. We'll put one vertex here at A0, whatever that is, and this one will be 0A. Okay. And let's suppose that density is proportional to, well, let's say the square of the distance. This makes things a little nicer. So that means, i.e., we could write rho of xy is equal to, let's say, some constant k times x squared plus y squared. Okay. So as you get farther away, you're going to multiply by k to get what the density is. Okay. So now we want to find the center of mass. And so I guess, that's going to be the question is, can you find, so I'm going to say this, start by finding x bar. And we'll turn you loose and see how that goes. You guys are welcome to work together on this if you want. It's not a bad move. What do we have to do? M, we're going to integrate the density function, double integral, right, where this is my region R of k times x squared plus y squared dA. And since k is a constant, we'll pull it out front. And now, it doesn't matter if I do dx dy or dy dx, right? I mean, it's the same thing. So let's do dy dx because I'm just more comfortable that way in general. X squared plus y squared. Let's fill in the bounds. So I guess, well, for the x's, we're doing numbers, right? So these are the boundaries, right? It's as we move dx and we get this little dx going on from here to here, it's x equals 0 to x equals what? A, I guess, right? Now the y's are functions of x. So the functions we're looking at, well, down here we have y equals 0, and up here this blue line would be y equals, wouldn't it be negative x plus a, right? Because it's a negative 1 slope. Yeah? Or I guess I could write it as a minus x, depending on how you like to write it. So we're going from 0 to a minus x there. Look good? Any questions so far? All right, here we go. K times, I'll do the first integral, I'll leave the second one here. So that first integral, let's see, we're integrating dy, so we get x squared y plus 1/3 y cubed. And this is from y equals 0 to y equals a minus x. So then I'm going to get k times, we need to integrate from 0 to a. Let's see, if I throw an a minus x in there, I have x squared a, well, x squared times a minus x, I'll put in parentheses, plus 1/3 a minus x cubed. Right? Dx. Okay, so now I have a choice. Do I expand everything, or do I use substitution? Okay. Let's substitute, right? I mean, actually, if it were me... What's that? You thought about expanding, or thought about...
No, I thought about substituting, but couldn't figure out it. Thought was substituting, so I didn't expand.
I mean, I guess the issue is, if you let u equal a minus x, the problem is this x squared then, right?
Yeah.
I guess, well, then you could solve, and you say, well, x is... But maybe the better thing to do... Yes, let's split it into 2. So let's call this one of the integrals we need to do is ax squared minus x cubed dx. And the other integral we need will just be, I'll put a 1/3 out front here. It's just a minus x cubed dx, right? So for this one, we're going to let u equal a minus x, and we're going to let du be what then? Negative dx. And so you'll need a negative sign to get it to work. Then what you end up integrating is u cubed du, right? and there'll be a negative sign out front because of that. Well, there already was a 1/3. So that's kind of what happens. So I think I can go through both steps pretty quickly now. Oh, and this should be not just 1/3 because there's a k. Let me call it k/3. All right, so here I go. So we have, or maybe I should leave the k out. Yeah, let's leave the k out front of everything. That makes more sense. Okay, so we have k times, and I'm integrating this one dx. So I'm seeing 1/3 ax cubed minus 1/4 a to the 4th, and that's from 0 to a. And then because there's a minus sign that came out, we get minus 1/3, and then times another 1/4 because it's u to the 4th, but the u was a minus x, so it'll be a minus x to the 4th. And again, that's from 0 to a. That's kind of interesting. Like when you plug in a to the first integral, stuff stays. When you plug in 0 for the oh, okay. There was a mistake, guys. Do you see the mistake? It was 1/4 x to the 4th here, because it was x cubed. Okay. So let's finish up. We have k times what? Well, all this stuff times k, right? 1/3 a to the 4th when you plug in the a, minus 1/4 a to the 4th. And then when you plug in a here, it's minus 0, right? And then you subtract, when you plug in your zeros, you have a 0 minus 0. But when you plug in a 0 here, it's minus 1/12 a to the 4th. So it's a whole bunch of a to the 4ths, right? It's, let's see, k a to the 4th times 1/3 minus 1/4 plus 1/12. 4/12, 5/12 minus 3/12 is 2/12. K a to the 4th, so 1/6 k a to the 4th. Huh. Very similar to the other problem, isn't it? Very similar to the other problem. Okay, so now we need my, the moment. New page? Yes, I think so. By the way. So now we're going to do my, right? The moment across the y-axis. And so that is k times the double integral of, again, over r dA. But this time, instead of just the density function, it's x times the density function, which was x squared plus y squared. So, let's see. This is k. Let's write this double integral out. Same limits, right? Yeah, same limits. Sorry, this was dA. Now I'm doing dy dx, and it's x cubed plus xy squared, because you multiplied by x. And let's see, we're going from 0 to a. And was this 0 to a minus x, if I remember right? I think so.
Yeah.
All right, so now we integrate at least the first piece. So I'll write the other one down. We have integral 0 to a dx stays there. And now we go x cubed y plus 1/3 xy cubed from 0 to a minus x. Actually, Yeah, well, let's do it. I'm already doing it. So this is k times what? Integral 0 to a. We throw in zeros for y, it all goes away. When we throw in the a minus x's, okay, it's kind of same deal, right? We get x cubed times a minus x plus 1/3 x times a minus x quantity cubed. All right, another decision to make. Should I split it into two integrals like I did last time? Or should I just expand it all out? Are you sure?
That's what I did, and there's got to be a better way to do it. I mean, I already had it expanded from
I mean,
step one.
expanding's not as bad as you think. I mean, it's a cubed minus 3a squared x plus 3ax squared minus x cubed, right? Oh, you don't have the formula memorized? I don't have it memorized either. I just know this. The binomial theorem, right. A minus x squared is a squared minus 2ax plus x squared. Because what's going on here, guys, it's the good old Pascal's triangle.
Yeah, I never remember that either.
Yeah, that'd be a good thing to remember.
Yeah, I probably should.
I think.
I have kind of a brute force method when it comes to foiling.
Are you guys okay that I do this? I really want to. I mean, because if I don't, what? It does work. If I don't, what do I have to do? I'm going to split them up again. And now I'm going to integrate by parts, maybe? No. I think I would. No, I don't like it as well. I like this better. So you okay with me showing the other right here? Let's do this. Let's use that fact. If I know that this is that, I just think I'm going to be able to do it more quickly and get us out of here on time. What do we have? 7 minutes? Yeah. So k integral 0 to a. All right, so let's see what's going on here. We have ax cubed minus x to the 4th. And then it's basically 1/3 x times all this stuff. So plus 1/3 a cubed x minus, see, look at that. This was made for this. The 3's cancel. Minus a squared x squared plus ax cubed minus 1/3 x to the 4th dx. Can that be simplified? Well, let's see. Yeah, there's some x to the 4ths here. There's some ax cubes here. And here. Oh, wait, no. Got confused. This one. That's an a cubed x. All right, so let's do this. Let's start off with the a cubed x. 1/3 a cubed x minus a squared x squared plus 2ax cubed minus 4/3 x to the 4th. How's that look? Not too bad, right? We doing okay? So now when I integrate, this is, let's see, 1/6 a cubed x squared minus 1/3 a squared x cubed plus. Now, this is 2, but we put it over 4, so we get 1/2 a x to the 4th minus 4/15 x to the 5th. Yeah?
Yeah.
All that from 0 to a. Okay. So isn't it true that all these things are going to be a to the fifth?
Yeah.
Yeah.
Cool. So we get k a to the fifth times a bunch of fractions. 1/6 minus 1/3 plus 1/2 minus 4/15.
Comes out to be 1/5.
Really?
Yeah.
So you're telling me that's 1/5 k a to the fifth.
Pretty sure.
Okay. And then I don't have it. On the other page, what did we have? We had little m.
1/6 K A to the 4th.
Okay, so x bar is 1/6 k a to the fourth divided by 1/5 k a to the fifth.
Oh wait, I
I'm not
think
sure
I
one
had
fifth is
something.
what.
Yeah,
I don't
it
think
is
it
us.
does.
We were trusting you.
Yeah, sorry. I'm not-
Okay, let's try again.
Yeah.
Let's see. What's the common denominator? 30, right? So I have 5/30 minus 10/30 plus 15/30 minus 8/30. So 20 minus 10 is 10, minus 8 is 2/30. I'm getting 1/15. That's what you meant, right?
That, no, yeah, sure, that's what I meant.
1/15.
Definitely what I
And since that's 1/15, so now the k's cancel, and I'm getting 15 over 6a, which is 5 over 2a. Yeah.
That came really simple.
So that's x bar.
Correct.
Okay. Time for y bar. Do we have time? Yeah. We have 3 minutes. Ready? Let's look back at the picture. I mean, I feel like you can tell by symmetry from the picture that isn't it true that the center of mass has to be somewhere on the line y equals x? Why? Well, because the picture is symmetric with, but not only that, the density function, if you switch, right? Rho of yx is equal to rho of xy. It really has to do with both the picture and the density function. And so, kind of like last problem, very carefully chosen when you have to perform in class. Of course, on the test, who knows? You'll have like horrible problems, right? So anyways, but the final answer would be, the centroid of this thing would be 5 over 2a, comma, 5 over 2a. It must be that x bar and y bar are the same value, right? And so that's your centroid. Wow. Done with a minute to spare.